Hey Ramblers. This video covers chapter 1.7 in our textbook and deals with continuity. So we've finished building our library of functions, and now we're going to look at an important property of many functions, which is continuity. So in this video we're going to define continuity. We'll look at some examples of continuous functions and non-continuous functions, and then we'll talk about an important implication of continuity called the intermediate value theorem. Now please, this is a short video but very important. The intermediate value theorem is one of the most important theorems in calculus. We're only going to learn about 4 or maybe 5 theorems this year. So this is a big one, and while not difficult to understand, it's important to recognize that it exists and to understand what it is. So think about this. If you were hiking up a mountain and you started at, let's say, 9 a.m. and you hiked up the mountain and maybe you crossed a stream, perhaps you stopped to fish for a while, maybe you took a nap, a few breaks, and you finally arrived at your campsite toward the end of the day. The next morning, you left your campsite at the top of the mountain and you went back down the hill. This time, since you're going downhill, you traveled much more quickly. Maybe you didn't stop to fish. Maybe you didn't need a nap this time. Do you know that there would be some point along the trip where you will be at the exact same point at the exact same time? It's true, and I'll explain why at the end of the video. Okay, Ramblers, take good notes, pause often, and thanks for watching. Okay, we talk about continuity in calculus relative to functions, and functions are continuous. In a very casual definition would be that you could draw the graph of the function without lifting your pencil, and that's absolutely true. But a function, kind of more technically, is continuous over an interval if there are no jumps, there are no breaks, and there are no holes over that interval. You could also describe the continuity over the entire domain if there are no jumps, breaks, or holes over the entire domain. So let's get that in your notes. Okay, so this means no asymptotes or no holes. Now, most continuous functions are pretty easy to imagine, but let's take a look at one of my favorite examples of a non-continuous function. And that would be f of x equals the absolute value of x over x. Now, the numerator is always going to be positive. So when we divide by the denominator, that quotient will equal 1 if x is positive, and so we'd have a kind of a constant function at 1. And if x is negative, that quotient will be negative 1. But right at 0, we're going to have a hole. So I'm going to put a circle there to show that there is a jump in the graph at 0. And in fact, there's also a hole in the graph at 0. So this would be a non-continuous function. All right, now let's take a look at what a continuous function would look like and why this idea of continuity is important. Okay, let's look at a function. We'll call it c of x. And c of x is just going to be a line. Nothing exciting here. And c of x is going to cross the x-axis, well, looks like it about -2. But what continuity means is that we know that if a graph is negative and somewhere in its domain, and it becomes positive somewhere in its domain, we know that somewhere the graph must have crossed the x-axis. And that's just a very obvious idea to us and not really worthy of a lot of attention, but it gets a lot of attention in calculus. And that's why continuous functions are important. That's an important property, that we know that it crosses the axis if it changes from negative to positive and the function is continuous. Unlike the example we just looked at, absolute value of x over x. That became positive without ever crossing the x-axis. Okay, so let's get this more formal definition of continuity of a function at a point. And you can see that a function is continuous if nearby values of the dependent variable give nearby values of the function. Okay, what does this mean? Well, let's take a look at a function, some kind of a jump function. All right, if we looked at the absolute value of x over x again,
with our jump at 0. As I got closer to 0 from the positive side, so I had 0.01, I know that my y value, if x is 0.01, then my y value is going to be 1. If x is 0.001, my y value is 1. If x is 0.0001, my y value is 1. But then I get, let's say I come from the other side, and I'm at negative 0.0001. What's my y value? Negative 1. If I get a little closer, negative 0.000001, my y value is still negative 1. So another reason that continuity is important is that it allows for, as you converging toward an x, the y values are converging toward a y. So take a look at this kind of shortened definition here. If f of x is continuous at a point, let's say x equals c, the values of the function approach f of c as x approaches c. So in other words, the function is going toward a y value from both sides as you approach x from both sides. All right, this sounds a lot like our definition of limit, and we're going to be more formal about that too. So for now, let's move on and talk about the intermediate value theorem. Okay, the intermediate value theorem, make sure this gets in your notes. Like I said in the introduction, it's about one of 5 theorems that we'll talk about this year, and it's really important. Luckily, it's simple to understand. It tells us that if you have 2 points on a graph, we'll call them A, f of A, and B, f of B. And k is any number on the y-axis between f of A and f of B. So anywhere in this range, there is some number k. Then there is at least one number on the x-axis, we'll call it c, that is between A and B, such that the point f of c is equal to k. Okay, it seems like a lot of work. It just means if you're going to get from f of A to f of B, you're going to have to take on all of the y values between f of A and f of B. Okay, in other words, if you are standing at the 10-yard line and you score a touchdown, we know that you at some point must have crossed the goal line. That's what the intermediate value theorem is all about. Okay, so let's go back to our backpacker problem. We said that if you left at 9 a.m. one morning from the base of a mountain and you started to walk up, and on your way up, who knows, maybe you're going slow because you're going uphill, so maybe you stopped to fish, then you kept going and you took a break for lunch, maybe toward the top you took a nap, and finally you get to the very top and you set up tent and you decide to rest for the night. The next morning at 9 a.m., bright and early, you decide to go back home. And you go down the hill. Who knows, maybe you go slower to enjoy the view. Maybe you're going faster because you're going downhill. Maybe you don't stop to fish. Maybe you do stop to take pictures. Doesn't matter. Either way, you left at 9 a.m., the same time that you had left the previous day. You must at some point end up at the same place at the same time that you had been going on the way up. Can you understand how that relates to the intermediate value theorem and why that must be true, that you're at the same place at the same time of day? Okay, in order to prove this, the easiest way doesn't take any calculus at all. Imagine that you're not just one person, but that you're 2 people, and you're both leaving at 9 a.m. on the same day. The person going up the hill, whether they stop and fish or take a nap or go directly up, at some point is going to bump into the person coming down the hill. And so at that point, you will be in the same place at the same time. So this theorem holds, and it really is an application of the intermediate value theorem. Okay, Ramblers, thanks for listening. And I thanks for watching too.